Hello, I'm Harold McNair. The first question is, what is gas chromatography? As we can see from this first slide, gas chromatography is a separation technique. Small amounts of sample, for example, 1 milliliter of air, 1 microliter of a solution, either of liquids or solids in solution, are injected into an instrument. The machine is called a chromatograph, a gas chromatograph. This machine, by using an injection port, a column detector, generates a written record of the analysis, a series of peaks. And those series of peaks are called a chromatogram. A chromatogram is simply a written record of the analysis performed by the gas chromatograph. How does this column and system separate things? This shows us a schematic of a GC packed column. There are two columns, packed columns and capillary. In this packed column we have two phases, a mobile phase which is moving, a stationary phase which is not moving. The mobile phase is also called a carrier gas, and typically it's helium, sometimes nitrogen, sometimes hydrogen. The carrier gas flows constantly through the column. Samples injected earlier are vaporized by a heated injection port, and the vapors are carried by the carrier gas into the column. Here those vapors will partition into this red stationary phase. The stationary phase is a high boiling liquid which has a very high partition coefficient for the samples. High partition coefficient, a high solubility. So we have to choose carefully that stationary phase so it will dissolve the sample. And we have different types of stationary phase for different types of columns. The vapors come in, they partition into the stationary phase, they come to equilibrium with the moving gas phase and come back again in a series of steps, absorbing, desorbing, absorbing, desorbing. Each of these steps is called a theoretical plate. We'll define this and show you how to calculate that schematically or through use of the computer somewhat later in this presentation. For the packed column, this tube is typically stainless steel or glass tubing in short lengths of 3 foot, 6 foot, sometimes as long as 12 foot. The GC instrument responsible for this separation consists of several components. A gas cylinder here, let's say of helium, a two-stage regulator, where the first stage shows you the gas pressure left inside the cylinder. The second stage is set by you, the operator, to sometimes 40 or 60 psi. This pressure then drives the carrier gas through an injection port, a column, and onto the detector. This injection port is heated. It is used to rapidly vaporize any sample which happens to be a liquid or solid at the room temperature. Once vaporized, the carrier gas carries it into the column where the separation occurs. After the column, the sample components enter a detector where an electrical signal is generated. That signal is proportional to the concentration of the sample. And that signal is recorded here on the data system. In today's world, this is almost always a computer. Earlier times we've used integrators, and much earlier times even a very simple recorder. Here we have a typical chromatogram. In this chromatogram we see two peaks here. We see the baseline here, where no peaks are occurring, and we notice two important things. The retention time here is used for qualitative analysis. Qualitative analysis, that is to say, what is that peak? The retention time is simply the time from the point of injection to the peak maximum, and that is characteristic of this column, this system, these conditions. The next important fact we see is the peak area. The peak area is used for peak concentration. Twice the concentration, twice the peak area. Thus this peak area represents the amount of sample which is present, the amount of that particular peak. One could also use peak height, and in third world countries where they do not have computers, oftentimes a simple ruler is used for measuring peak heights. But in the modern world with computers and integrators, peak area is easily obtained and the results printed out on a report. What are the advantages of GC? Because GC is one of the most popular instruments used in the world. Several advantages include high resolution, high speed, high sensitivity. High resolution, many compounds can be resolved nicely. For example, gasoline has been resolved into over 300 different peaks, a very complex sample of petroleum. High speed analysis in a matter of minutes are routine, and in the last few years, analyses in a matter of a few seconds are also possible. With high sensitivity, we see both rapid analysis as well as high sensitivity. Here, for example, is a 2.5 minute separation of 3 common pesticides: methylparathione, malathione, and ethione at the picogram levels. Picogram, 10 to the minus 12 grams, means these are parts per billion. So this is a very good example of both a high speed as well as a very sensitive detection. High accuracy. Accuracy just means when we do quantitative analysis, we get very good results, the right answer. Good quantitative results. GC is also a fairly easy technique compared to some fairly well known. I mentioned earlier, probably one of the most widely used instruments in the world today. But we must be honest, there are also limitations. GC, the samples must be volatile. We are allowed to heat the sample up to 300, 350 degrees centigrade, but at that point we must generate vapors that can be easily carried by the carrier gas. Dirty samples require cleanup. I think of a dirty sample as urine, wastewater, extracts of many things, in that these samples will not only contaminate the system, they may even, plug up the column, destroy the column. In this case, oftentimes we will extract or use a solvent to take out the important components. Another limitation is we must use another instrument, for example, a mass spectrometer for confirmation. Typically, we use that retention time described earlier, the retention time of standards and unknowns, to decide what the peak can be. But legally, at least in the United States, retention times are not considered a confirmation. A mass spectrometer is needed for confirmation if necessary. And finally, of course, some training, some experience is necessary in order to obtain good results. Samples for GC, they can be gases, and to my knowledge, almost every gas has been analyzed, liquids, and some solids. Solids are usually dissolved in a low boiling solvent and analyzed. Molecular weights have been done easily from molecular weight of 2 hydrogen up to over 800. In exceptional cases of simple hydrocarbons, molecular weights up to 1200 have been separated. Samples can be organic or inorganic, but most of the work with gas chromatography are organic compounds. Typical examples of inorganics would be water or gases. The sample, however, always must be volatile. I like to say you cannot do rocks or sticks or stones. You can also not do proteins, peptides, biological molecules. Those are better done by liquid chromatography. For quantitative analysis, I mentioned earlier that we use the peak area being proportional to concentration, and I'd like to show you some data here. This is a very simple sample of hydrocarbons, decane, undecane, dodecane, tridecane, which were blended up volumetrically, and using the density, I calculated the mass in grams. This is what was determined by gas chromatography plus 1 standard deviation, and the results showing relative error less than 1% in all cases. This is a simple sample done by flame ionization together with the aid of a computer, but it is typical of the very high accuracy one can obtain. Thus we see quantitative analysis is one of the major advantages of gas chromatography.